Today we're going to learn about slightly more complicated inequalities that we're going to create by sort of stitching together simpler inequalities, combining them in a few different ways. The good news is the individual pieces that we're going to be stitching together are pieces that we should already be fairly familiar with. The first type we're going to take a look at is one that's fairly easy to understand intuitively. It goes together with the word between. When you use the word between, you're really saying two inequalities at the same time. Like in this example we have here, this thing in the middle, x plus 2 over negative 5, it is between negative 2 and 6. And what that means is both bigger than negative 2 and also smaller than 6. So it's really two inequalities at the same time. The way you solve it, the actual algebra of solving it, is luckily pretty much identical with one twist to the way you would normally solve an inequality, or for that matter, how you would solve an equation. Here we have a fraction floating around in the problem. It has a denominator that we'd like to get rid of, so we're going to multiply everything by the denominator. Now normally, when you multiply everything by the denominator, you have a left side and a right side you have to multiply. But here we don't just have a left side where we have to multiply by negative 5 and a right side where we have to multiply by negative 5. There's also a middle here in the middle that we have to multiply by negative 5 as well. And that's the twist. That's the only thing that you got to keep in mind when you're working these problems. There are three sides. Don't lose one of the sides. And this happens because people are so used to doing two-sided equations and two-sided inequalities that their subconscious just refuses to believe there's a third side, and they sort of develop a blind spot. I've seen lots of homework and test questions where students will be doing a problem like this, and one of the sides just disappears for no good reason. They just don't keep track of it. Here, as long as you keep track of all three sides and do normal algebra, you're going to get to the right answer. So here, negative 5 times negative 2, what would you normally get? 10? Well, you get 10, just like normal. 6 times negative 5, wouldn't you normally get negative 30? Yep, just like normal. And when you multiply a fraction times the same denominator, the denominator and that number cancel out, and you just get the x plus 2 by itself. So if you lost the 10, or if you lost the negative 30, or if you lost the x plus 2, if one of those disappeared, your answer is definitely going to be wrong. So the real trick here is to keep track of all three parts of the problem. Now, there are other tricks that are just normal algebra tricks, like, for example, in this problem, we multiplied through by a negative, so the inequalities have to change their direction. They have to end up pointing the other direction because we multiplied by a negative. Now, that's not new, that's a perfectly normal sort of a thing. The other perfectly normal sort of thing that you usually have to do is you're not allowed to leave that as x plus 2. You got to get it to be x period. So we're going to subtract 2. And again, there are three sides. If you're going to subtract 2, you got to subtract it from all three sides. The middle and the left and the right all have to get subtracted 2. So this side's going to be 8. This side's just going to be x. And this side's going to be negative 32 now. Now, this is not an acceptable answer. We're not done with this problem. We still have to put it into the right format for an answer. The answers to these things usually go one of two ways. Either you're asked to draw a graph, or you're asked to put the answer in interval notation. Interval notation is probably the more common one. Just about every textbook uses interval notation. Just about every homework problem will use interval notation. All the teachers I know use interval notation. But the graph is probably the better place to begin because it's where you catch a lot of little mistakes that otherwise could slip past you. Plus, the graph sort of makes more intuitive sense anyways. So here, for graphing the answer, we're going to have two boundary points for this problem. 8 and negative 32, those are our boundary points. So you draw a number line, you put in a couple of boundary points, and then there's another really common mistake a lot of students make. This mistake happens when a student gets going too fast and they're not really paying attention, they're in too much of a hurry. Take a look at what happened there. And I can tell you how this happens. If you look at the numbers back over here, 8's on the left, negative 32 is on the right. So when people write it into their number line, they put 8 on the left and negative 32 on the right. But stop and think about it for just a second. Isn't negative 32 a negative number? Isn't 8 a positive number? How is the positive number on the left and the negative number on the right? That's clearly backwards. So if you just think a little bit, just stay awake while you're working the problem, put numbers in their natural order. Smaller numbers to the left, bigger numbers to the right, like usual. The x that we're looking for here, the solution set, is the stuff that are between those numbers. So that's this stuff in here. And then pay attention to the inequalities to tell you what types of dots to put at the end. 8 is not included, so we use an open dot. Negative 32 is included, so we use a filled in dot. Once you have the graph drawn up, getting the interval notation is very simple. The left end is at negative 32, the right end is at 8. We're including the negative 32, so we use brackets. We're not including the 8, so we use parentheses. That's the interval notation part. It's very easy to do if you've done the graph first. Now, this between type of inequality is not the only type of inequality. It's not the only way that we could combine inequalities. There are more complicated ways to do this. So let's take a look at another type of situation. Another type of situation where you combine inequalities involves writing down two separate inequalities with a word in between them, either the word or the word and. Now in this case, they're the same inequalities in each case because I don't want the solving to be the part. I want everybody to focus on the word in the middle. There's a little bit of solving, like here you got to multiply by -1 to clear out the negative sign on the x, and you're going to end up getting x is bigger than -1, and it would be exactly the same over here. And the way you typically do these word in between problem types is you just treat the two inequalities as if they are just completely separate inequalities. And then you graph them up as if they are two completely separate inequalities, like x less than or equal to -7. Well, that looks like this. X greater than -1, that looks like that. And you would get the exact same picture over here in this problem. That's one of the things that's a little funny about these problem types with the and or the or. You don't really care what the word is until you get to the very end. You do all the work exactly the same until you get to the very last part of the problem. So here's where the difference comes in. When you got the word or means that you need to include everything that's in either one of the inequalities. You don't have to try to do both the one and the other. Like here, in order to be a part of the solution set, a number does not need to be smaller than -7 and at the same time bigger than -1. Here, if a number is smaller than -7, it gets included in the answer. So all of this stuff is part of the answer. All of this stuff is also part of the answer. And then to say that this is really one big answer to this one complicated question, you put the union symbol from set theory in between. So anytime you see the word or in one of these multi-part inequality problems, what it means is to take everything, include everything from either part. Now, let's take a look at the one on the right. Things are very different here. It's got a different word. It's got the word and. And means you have to solve both inequalities at the same time. If you're an answer to this combination inequality, then you are both smaller than -7 and you are also bigger than -1. And if you stop and think about it, there are no numbers anywhere that do both of those at the same time. There is no solution that can be smaller than -7 and also bigger than -1 at the same time. Anytime you see the word and, in one of these combination inequalities, what it means is take the overlap. Where do the two parts overlap? And sometimes they'll overlap, sometimes they won't. If they don't overlap, then there's no answer. There's no solution. You write no solution. Okay, so let's take a look at some trickier cases, because this one, the actual solving part was pretty trivial. There wasn't much solving that we had to do. It was just how to use the word and to use the word or. And depending on how much work goes into the solving and what the inequalities look like when you're done, these can get trickier. There are some tricky cases we have to deal with. So let's take a look at this one. It's got a word in the middle. Remember, the word doesn't really matter until we get to the very, very end. We treat each inequality as if it's a separate inequality, and we solve it all by itself. So like this inequality here on the left, we're going to subtract 3 from both parts. And that's going to get us a is less than or equal to -5. For this inequality, we're also going to subtract 3 from both parts. Solving it's pretty similar. And we're going to get a is less than -1. And then we graph up the two inequalities as if they were just two independent inequalities, as if they had no relationship with each other at all. A less than or equal to -5 looks like that. A less than -1 looks like that. And then at the very, very end, you suddenly pay attention to the word in the middle. Here, the word is and. Remember what and means, right? At the top of the screen, and means your solution is the overlap of the two. So we've got these two inequalities that are both pointing off to the left. There's this little region in here where only one of the inequalities is sort of laying on the number line. But here you got two layers. You've got both inequalities. So the overlap here is the stuff from -infinity to -5. That's our solution set. And just for comparison, just to make sure we're considering all possibilities, let's think about what would happen if it said, what if it said or instead of and? Well, or doesn't care about overlap. In fact, if they don't overlap at all, you still get answers. With or, you include everything, whether it's overlapping or not. So here, you would still include all of this stuff because you're including everything, so you're definitely going to include this stuff below -5, but you're also going to include this stuff in here all the way up to -1. So the solution set for this doesn't stop at -5. It goes all the way up to -1. If you're including everything that's in the overlap or not, you can include all the way up to -1. So the word in the middle, and versus or, makes a pretty big difference. It can be pretty vital in what your solution is when you're all done. Now, this one here is going to be a little tricky. Part of what makes this problem trickier is the fact that as we are solving each one of the two inequalities, they involve a little bit more work. Here, the two inequalities we're working with are more involved. Like this one here on the left, we're going to have to add 7 on both sides. That's going to give us a 3b is greater than -3. And then we're going to divide both sides by 3. Stop and think. Does that mean we're going to change the direction of the inequality? No, because what we've divided by here was not a negative number. There is a negative number in the problem, but we did not divide by a negative number. We didn't introduce a negative number into this problem. So the inequality's direction does not change. Okay, so there's the left inequality. A little bit more complicated than the ones we've done earlier. Similar steps over here, subtract 2 on both sides. We've got 5b is less than or equal to 20. Then we divide by 5. Again, it's dividing by a positive, so that's not going to cause us to change anything. So we've got this. And then we go ahead and do our graph. So let's see. B greater than -1 is all of this stuff. B less than or equal to 4 is all of this stuff. And now we pay attention to the word in between. It's the word or. And remember how or works. OR takes everything. It doesn't care whether there's overlap or not. So here, if you look at this picture we've drawn up, at least one of these inequalities, sometimes both inequalities, but at least one of these inequalities hits every single number on the entire number line at some point. There is no place that these two inequalities don't eventually cover up somewhere. If it said and, things would be pretty different. If the word here was and, the overlap is just the stuff between -1 and 4. And is where you take the overlap. But it doesn't say and, it says or. And when you're doing or, you take everything regardless of whether it's overlap or not. And here, everything means everything. We would get all the numbers from -infinity up to +infinity. That is actually an answer that you can put to some of these problems sometimes. Now, if you happen to be the kind of person who likes fancy notation and you just think it's kind of cool to learn new and fancy symbols, there's actually a math symbol specifically for the whole collection of all the real numbers all together. And it looks kind of like a big capital R with 2 vertical lines in it. So if you're on a test or something and you'd like to use this fancy symbol for all real numbers, please feel free. I kind of enjoy learning fancy, goofy little symbols like that. So if you're the same type of person and you think that's kind of cool to know that symbol, you can use that. That is a way of saying all real numbers are an answer. It's a little more straightforward, a little more regular to say -infinity to +infinity, but you can also use the big capital R thing. Now I've got one more really complicated example to show you. And it's not going to look all that complicated. This is sort of a stealth example. Everything looks pretty normal at first, and then it gets very weird right at the very end. So again, yeah, there's a word in the middle. It's the word and. Don't worry about that. We don't pay any attention to the word in the middle at first. We treat it as if it was 2 homework problems, and you just solve each inequality all by itself. Oh, I just realized there's a typo here. Let me fix my typo. These are supposed to be or equals inequalities, and you're going to see at the end that makes a massive difference. Okay, so let's go through the solving process and see what we get for our answer. So we add 1 on both sides here with this. We get 2t is greater than or equal to 6. Then we divide by 2, and we get t is greater than or equal to 3. We didn't divide by any negatives, so we don't have to worry about changing any directions or anything like that. We just solve that without having to worry about directions. This one's going to be a little different. We're going to subtract 2 to begin with. That's going to give me -3t is greater than or equal to -9. But then we are going to have to divide by -3. And this is the situation where you have to change the direction. We divided by a -3. -3 is something that we chose to use as part of the solving. So the inequality has to change direction and end up pointing that way. And then -9 over -3 is +3. Then we go to graph up our 2 inequalities, and this one is t bigger than or equal to 3. So that's this stuff here. And then this inequality is t less than or equal to also 3. It's got the same boundary point as the other one. Huh, okay, that's a little weird to have the same boundary point. But if you think about it, that's not impossible. That's just got to be really rare. I mean, that's got to be, what a coincidence that you end up with the exact same boundary point for each of the inequalities. But it can happen. It's not impossible for that to happen. But what's really weird is the overlap. Because remember, this is the word and only takes the overlap. So what's the overlap here? Well, just 3. I mean, not from 3 to something else, not from something else to 3. There's not like a whole region of overlapping stuff. There's just one individual number all by itself. So the overlap here is just the number 3. So how are we supposed to write that? I mean, it's not like you can use interval notation. There's not like a left end and a right end. There's just a single number all by itself. So this is, although rare, this is a possibility. And when you are doing interval notation for a single individual number all by itself, not truly an interval at all that doesn't go from something to something, but a single number all by itself, this is where you use the third type of parentheses. So in interval notation, you've seen us use square parentheses and round parentheses, but we also use those sort of cursive, curly, wiggly parentheses as well. The wiggly parentheses are for isolated individual numbers all by themselves. And that can happen. It's incredibly rare, but it is a possibility with an AND problem where the inequalities point two different directions, but they share the same endpoint and they include the endpoint. Then maybe you might get a single isolated number all by itself and have to drop with the curly parentheses. Okay, I have shown you all the complicated cases you're going to have to worry about here in section 9.2. Of course, inequalities will get more complicated in the future, but for this section of the book, you're good.